This is part 2 of a series I'm doing on gravity. Last time we talked about the centrifugal force created by the spin of the Earth. Today, let's dive into density and buoyancy. If you've paid any attention to the flat Earth movement, you've encountered claims like, gravity doesn't exist, gravity is just a theory, and it's just density and buoyancy. Before I go on, let me pause to talk about the target audience for this video. If you're a flat earther or flat earth curious, and you think there could be some validity to the density and buoyancy idea, this video is intended for you. I hope to show that you do not need to reject gravity outright. In this video, I intend to show how gravity is related to buoyancy without making any assumptions about the shape of the Earth. If you really want to be a flat earther, you can still accept most of gravity. You don't need to go around saying, there's no such thing as gravity. I'm sure you've seen the reaction that gets, and I'm telling you, you can do better. If you're one of those flat earthers who has already figured this out, great. This video will be boring and condescending. Maybe you believe in universal acceleration. Well, at least you've gotten that far, so great. Maybe we'll cover that one in a future video. For today, I'm giving you a pass. So if you're a flat earther watching this, I get it. You don't trust me. You're inclined to disregard anything I have to say, but I'd encourage you to give this a try. I really can help you here. I'm about to show how density and gravity work together to cause the effect we call buoyancy. I'm going to explain how this part of the gravity discussion works just fine on any shaped Earth you believe in. Let's dive into the concepts of density and buoyancy and try to evaluate the basic claim that everything is explained by density and buoyancy. Just how far can we get with nothing more than density and buoyancy? Let's start with some definitions. What is density?
I'm your density.
Maybe you answered, density is how heavy something is. If so, you're close. Weight is the measure of heaviness. Density is related to weight. Consider these bottles of water. The big one is obviously heavier than the little one, and yet they have approximately the same density. Density is defined as mass per unit volume. They're both water, so they both have the same density, but there's a lot more water in the big one, so it's heavier. The little bottle holds 8 fluid ounces of water, and the big one holds 5 gallons. That makes it 80 times heavier. Heavier, but the same density. How would we go about measuring density? There are a few approaches, but I think the obvious one is to measure mass, measure the volume, and then divide them. Mass per unit volume. That's just mass divided by volume.
Excuse me. Would you mind stopping that noise?
No, not that kind of volume. We mean how much space something takes up. To measure the volume of a liquid, we can just pour it into a graduated cylinder. Measuring the volume of a solid is a little bit more involved, but there's a useful trick. If you dunk a solid completely under a liquid in a graduated cylinder, the liquid level will rise. The solid pushes some of the liquid out of the way, and the liquid level goes up by the exact volume of the solid. Measuring the volume of a gas is tricky because the volume of the gas tends to expand to fill whatever container you put it in. Gases are compressible, meaning their density can be changed very easily by squeezing them. If any flat earthers are watching my channel, that was a pretty good cherry pick opportunity right there. You may want to use that clip to show how the atmosphere cannot exist next to the vacuum of space. That's completely wrong, of course, but that's another video. The point is, this makes the question of density a little more complicated for gases. If you have a gas in a particular container, like a balloon, just measure the volume of the container. Okay, so we've got the volume of your object. How do we measure the mass? This can be a little tricky, so take a moment to think about this. Did you say you'd weigh the object? That's not bad. Honestly, that's my preferred answer as well. but we need to be careful with it. As long as the object is relatively dense, just drop it on a scale and you can get a reasonably good estimate of the mass. I'm afraid I need to get a little nitpicky here. Technically, scales do not measure mass. They measure weight. Weight and mass are not the same thing. They are closely related. But this is kind of important in the topic we're covering right now, so we can't let it slide. Recently, I was watching a debate where a flat earther refused to use the word weight. He clearly had some idea that weight was related to gravity, so he flatly refused to use either term. He was afraid he'd get caught admitting to the existence of gravity. What I'm trying to explain here is that doesn't make you look smart. If you don't want people making fun of you, don't act like this. This video is all about how you can still have weight and gravity on a flat Earth. And being defensive about it just highlights your obviously motivated reasoning. Weight is a force. We measure forces, like weight, in newtons or pounds. Mass is not a force. We measure mass in grams or kilograms. In the imperial system, we can measure mass in slugs, or pounds mass.
That's horrible. It's disgusting.
The slug is an amusing name for a unit of mass, but most people seem to prefer pounds mass. 1 pound mass is the amount of mass that weighs 1 pound. Hold up there, cowboy. My bathroom scale measures my weight in kilograms. Yeah, it surely does. Just like the pound mass is the amount of mass that weighs 1 pound, your scale is reading out the amount of kilogram that would weigh the same as you do. The bathroom scale technically isn't measuring your mass at all. It's measuring your weight. Then it makes an assumption about the relationship between mass and weight to read out your estimated mass. What's so different between weight and mass? Does that really matter? Or is this just a semantic argument? Well, what would you say are the differences between mass and weight? If your high school physics class is still fresh in your mind, I'm sure you can name several differences. What can you come up with? Here's what I've got. First, the units are different. We use kilograms for mass and newtons for forces. Under normal gravity, 1 kilogram weighs about 9.8 newtons. That doesn't really seem all that important, but it could bring further insight into the more interesting differences. Next, let me point out that force has direction, but mass does not. This point is subtle enough that it may seem frivolous. Mass is not weight, but mass does have weight. The other big feature of mass is inertia. F equals ma. That m there, that's mass. Let me rearrange for emphasis. A equals F divided by m. Force causes acceleration, and mass resists it. When you apply a force to an object, it accelerates in that direction, whatever direction that is. And whatever direction that is, mass resists that acceleration. Force has direction, acceleration has direction, but mass works in every direction. Mass has no direction. Next, we say that weight is the result of gravity acting on a mass. But it isn't really quite that simple, is it? In the previous video, we showed how centrifugal force plays a part. In practice, we just bake the centrifugal force into what we call gravity, but that means gravity is slightly different in different places. And that means the same mass will have different weights in different places. If you're still clinging to the idea that gravity doesn't exist, it probably means very little to you. But there's more. Try to measure the weight of a helium balloon to see what I mean. When we place an object on a scale, we are measuring the force of gravity pushing down minus the force of buoyancy pushing up. Here we are. We finally got to buoyancy. Buoyancy is really interesting. The science deniers like to claim that buoyancy disproves gravity. But does it? Okay, you already know I'm going to say it doesn't, but let's go through it anyway. What is buoyancy exactly? We know that dense objects fall to the ground, while especially low-density things, like helium balloons, float up. What's going on there? Remember when we dunked our object in a liquid to measure its volume? Where did that liquid go? It went up, right? You bet it went up. That liquid has a weight, and that weight got lifted up. The weight of that liquid is still pushing down. The liquid very much wants to get down underneath that ball, but the only way to do that would be to push the ball up out of the way. The liquid tries to push that ball up with a force exactly equal to its own weight. Dropping the ball into the liquid lifted the liquid up, and the amount of weight that ball lifted is still there, trying to lift the ball. I like to think of it like this. Fill a U-shaped tube with liquid and put a plunger on each end. Now, let's drop a weight onto one side. That weight pushes down on the plunger. So what happens next? The liquid level rises on the other side. The weight of the ball is pushing down on the left side, but it stopped sinking. If the motion of the ball stopped, that means the weight of the ball is being supported by an opposite force. On the right side, the weight of this water has been lifted up, and that weight is now pushing down. The pressure of that extra weight on the right side is pushing up on the ball on the left side. When the weight of the liquid on the right exactly matches the weight of the ball on the left, everything is stable. Buoyancy is like that. When an object is submerged in a fluid, the fluid it displaces has a weight, and that weight is still pushing down. That weight counteracts a matching amount of weight from the submerged object. So there you go. Dense things sink, light things float. It's all density and buoyancy, right? Hold on just a moment now. We just talked about the buoyant force. If you were paying attention, you heard how the buoyant force is caused by gravity. I know, I'm kidding myself. You didn't get that at all. So let's take a closer look. Look closely at that ping-pong ball right at the top. It's floating, but it isn't just resting on the surface of the oil, is it? No, it's actually sunk into the oil just a little, isn't it? Why did it sink in a little bit? How much did it sink in? How can we answer these questions? We answer those questions by understanding what buoyancy is. Sure, buoyancy means light things float in dense things, but we can say more. Buoyancy is a force that acts in the opposite direction of gravity. Here is the equation for buoyancy. The buoyant force is equal to rho GV. Rho is the density of the medium. G is the acceleration due to gravity, and V is the volume displaced in the medium. Notice the minus sign, indicating that the force of buoyancy points in the opposite direction from the force of gravity. Let's apply the buoyancy equation to estimate how far the ball will sink into the oil. A ping-pong ball has a mass of 2.7 grams. That's 0.0027 kilograms. Lamp oil has a density of 0.81 grams per cubic centimeter. That's 810 kilograms per cubic meter. The ping pong ball will be balanced when the force of gravity pulling it down is exactly matched by the buoyant force pushing it up. Let's use 9.80 meters per second squared for the force of gravity. The gravity pulling the ball down is 0.0027 times 9.8, which comes to 0.0265 newtons. If we set that equal to our buoyant force, that gives us a displacement volume for our lamp oil. 0.0265 equals 810 times 9.8 times V. Solve that for V and we get V equals that. That's a tiny looking number, but it comes out to 3.34 cubic centimeters. That's how much of the lamp oil needs to be displaced to hold up the ping pong ball. How much of the ping pong ball sinks? The radius of the ping pong ball is 20 millimeters. That's 0.02 meters. The volume of a sphere is 4/3 pi r cubed. So that gives us a volume for the entire ping pong ball of 33.5 cubic centimeters. The 3.34 cubic centimeters of lamp oil that get displaced as a fraction of the entire 33.5 cubic centimeters of ping pong ball comes to this, or just about 10%. So a ping pong ball should float in lamp oil with 90% of the ball floating above the surface. The force of buoyancy balances the weight of the ball, and the force of buoyancy was caused by the weight of the displaced oil. Remember, buoyancy is caused by weight, and weight is caused by gravity. So buoyancy is caused by gravity. Yes, the ping pong ball floats because it's less dense than the lamp oil. The relative density tells us that the ping pong ball should float. Hopefully, now we understand that the buoyant force has balanced the force of gravity pulling on the ping pong ball. We see that density is not a force all by itself. Weight is a force. The amount of weight is the mass times gravity. Buoyancy is related to density. Buoyancy is density times volume times gravity. Here's a video from Cody's lab showing an anvil floating in mercury. You should now be equipped to tell us how much of the anvil will float. You just need the density of mercury and the density of iron. If you also know how big the anvil is, you can work out how much weight it can support before it sinks completely. How hard is Cody pushing on the anvil here? Are you prepared to do that calculation? I'm willing to bet that if you started off saying there is no gravity, none of this has changed your mind. If you've been able to follow the math so far, you may have noticed that G canceled out of our ping pong ball calculation. Aha! Told you there's no gravity. Now, I mentioned this before, but I didn't actually show it during the calculations. The G is where we got the direction for our forces. Weight pushes down because gravity points down. Buoyancy lifts up because it's opposite to gravity. What if we could alter the direction of the effective gravity? Impossible? Did you forget the video on centrifugal force? Centrifugal force acts just like gravity. We can use it to create the exact same effect. Here's a video showing what happens to buoyancy when you apply a centrifugal force. You can see there's a little piece of foam floating in the jar of water, and something heavy that sinks. What's going to happen to these when he turns in a circle? You probably guessed that the bit of metal would be pulled to the outside of the circle, but notice how the foam was pulled inward. What's the point of this? This shows very clearly that the direction of weight and the direction of buoyancy are caused by the direction of the force field. To see the effect of buoyancy, we must have a force field. We need gravity to provide that force. Let's try this another way. Here's Smarter Every Day. He's got a helium balloon tied to the floor of his van. He's going to accelerate. Based on what we've learned so far, what do you expect that balloon to do when he accelerates? Make a prediction based on the scientific principles as you understand them. Now let's watch to see whether your hypothesis was correct. Now he's about to hit the brakes. What will the balloon do? Was your prediction validated? If you understood the concept of how gravity causes buoyancy, you can see that when Destin accelerates, that creates a force field within the van pushing backward. You are pushed backwards in the seat when you accelerate. The air in the van is pushed backwards too. The denser air is pushed to the back of the van, and that denser air shoves the helium balloon out of the way, forward. When you hit the brakes, everything reverses and the denser air shoves the helium balloon to the back. Once again, the direction of the force field determines the direction of the buoyancy force. So that's two different ways to demonstrate changing the direction of the local force field. What if we could remove the effect of gravity altogether? Here we see the classic example with different liquids of different density. But this time it's on the vomit comet. I've been going on and on about how it's gravity that separates these liquids. What's going to happen when the aircraft goes into free fall? Make your predictions. Here we go. the layering effect is completely eliminated. Dense liquids sink in light liquids, and that effect is caused by gravity. If we eliminate the gravity, we eliminate the buoyancy with it. Finally, I wanted to address the misconception that gravity is somehow selective. This is a common claim among the anti-gravity crowd. This meme illustrates the misconception fairly well. Here we have a bird that experiences a relatively small force from gravity, and an ocean that feels the weight of, well, an entire ocean. What makes gravity selective like this? Let me show you the equation for weight again. Weight equals mass times gravity. That F sub g there, that's the force due to gravity. That's the weight. I've got a little arrow on my F sub g to indicate that it's a vector, meaning it has a magnitude and a direction.
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
The m is for mass, not the weight, the mass. And the g is for gravity. The g has an arrow on it, meaning that it has direction. Gravity points down. The F sub g is the weight. Weight is a force. Force equals mass times what? Force equals mass times acceleration. So g is not a force, it's an acceleration. I think this is the root of this misconception. We often say gravity is a force, but if we want to get really technical, it's an acceleration. In this video, I'd sometimes refer to gravity as a force field. I know that sounds a little weird, but it just means we don't measure g in newtons. It isn't a fixed amount of force. The force isn't the same on every object. When we talk about gravity as a force, we're talking about the weight. The weight is the force caused by gravity. That little g there isn't a force. That's an acceleration. The amount of force this imparts on any object grows depending on how much mass the object has. Centrifugal force works exactly like this too. The centrifugal force we feel when we spin on a merry-go-round is larger for massive objects and smaller for light objects. Technically speaking, G is a force field. More mass means more force. Less mass, less force. The bird weighs less than the ocean because it has less mass. This isn't gravity being selective. Gravity is consistent. All masses are pulled down with a force proportional to their mass. Even helium balloons feel gravity. The weight of the air around them just feels it more. That's not selective. That's the consistent way gravity is applied to everything. Let me wrap this up here. You'll notice I didn't make any mention of Einstein versus Newton. I'll save that for another video. I also didn't mention how mass attracts mass or the Cavendish experiment. For this video, all I want you to take away is to stop saying that gravity doesn't exist. It just makes you sound silly. It makes you sound like you don't know what you're talking about. I get what you're trying to say. All you're trying to say is that gravity points down, and down is down, the same everywhere. So stop saying that there's no gravity. You'll make a much more intelligent argument if you just say gravity points down. Let me lay out the script for you. Try this. Of course gravity exists. Weight is caused by gravity pulling things down. Buoyancy is caused by gravity and causes dense things to fall and light things to float. We don't know what causes gravity, but we can measure the force of it, and it always points down. See, as a flat earther, all you need to say is that you believe gravity points down. Stop saying there is no gravity. I know you've been told that gravity disproves the flat earth. Don't let that sucker you into throwing out all of gravity. We'll get into aspects of gravity that don't work on a flat Earth in a later video. For now, all you need to know is that you can embrace the most obvious and undeniable aspects of gravity without having to accept that the Earth is a globe. It won't make you right, but at least you'll sound a little more reasonable.